we're starting section 3.2, and it is dealing with quantitative chemistry, or the numbers of chemistry still. And today we're going to look more specifically at the mole. So we've done the POGIL and the activity and talked about what a mole is, and now we're going to look at how it is used to do conversion. So first, quickly, we'll just review what the mole is. The mole is Avogadro's number, and it tells us how many of something there is. So if we have 1 mole, we have 6.02 times 10 to the 23rd of that thing per mole. So that's what this -1 power means on the mole. It means that the mole is on the bottom of the fraction. So we could say we have 6.022 times 10 to the 23rd atoms per mole. Or we have 6.022 times 10 to the 23rd molecules per mole. This is the number that we have per mole. Remember, it's like a dozen of something. There's 12 in a dozen. There's 6.022 times 10 to the 23rd in a mole. So we're going to use that to do some conversions. The most helpful thing about a mole is that it allows us to tell how many of something are in a sample by its mass. Okay, there is no way for us to count atoms, but if we can measure the mass of a sample, we can relate that to how many atoms are in the sample. For example, 1 mole of neon has this many, right, Avogadro's number of atoms, and it weighs 20.18 grams. So this fact that 1 mole, which is this many atoms, is this many grams, is going to allow us a lot of power in terms of figuring out how many atoms are in a sample. So if we have some neon that weighs 10 grams, then we can say that there's about half as many of these atoms. If we have a sample that weighs 40 grams, it's going to be about twice as much of 6.022 times 10 to the 23rd. Same thing can happen with something like an ion. Chloride ions. If you have 1 mole of those, then you have that many ions, Avogadro's number. And the mass is just the mass from the periodic table. Remember, a chloride ion negative means it gained an electron, but electrons don't have any significant mass, so the mass will stay the same. These mass numbers that we're looking at, they are called molar masses, and they come from the periodic table, and they represent the mass of 1 mole. If you remember in the last lesson, we found the molecular weight of substances, or the formula weight, from the periodic table. So we would look up, for example, for CO2, we look up carbon as 12.01, and oxygen as 16.00. We're multiplying by 2, because we got 2 oxygens. Right, so then we just add those together, and it turned out that it was 44.01 AMU. Remember, that means atomic mass units for every CO2 molecule. So if you had 1 CO2 molecule, it would weigh 44.01 atomic mass units. Now, an atomic mass unit is really, really small. We don't have a scale for that. However, we can find the molar mass. That is the exact same number, but instead of being the weight for 1 molecule, it is the weight for 1 mole of CO2. And remember, we know how many are in a mole. So 1 mole of CO2 weighs 44.01 grams. And we can weigh that on our scales, and we can figure out how many molecules of CO2 are in there. So these things are all equal. 1 mole, Avogadro's number, and then the mass from the periodic table. All right, so based on that, we can use our mole map to solve problems. So hopefully you have a copy of this, but this mole map is going to be your best friend as we go through this chapter. Hopefully I can expand this. My video's stuck. All right, now I got it. I'm back. So here we have moles in the center. I'm going to call this the mole map. I'll say that all the time. But we have moles, and we can go from moles to grams. Okay, and to do that, we're going to use this conversion factor. A conversion factor is just a fraction that allows us to move from one unit to another. So on that fraction, you always have the unit that you're trying to move away from on the bottom because it's going to cancel, and then the unit that you're moving toward on the top. So you can see if we want to go from moles to grams, we're going to put the molar mass, that's what that MM stands for. The molar mass in grams, that's from the periodic table, on the top, and then we'll just put 1 mole on the bottom because 1 mole is equal to the molar mass from the periodic table. To go the opposite way, we'll put 1 mole on the top because we're trying to move 2 moles, and we'll put the molar mass in grams on the bottom. So that's how we would do those conversions. If we wanted to move from moles to really any type of particle, so that could be particles, atoms, molecules, formula units, that could also be ions or electrons, really anything we're moving to, we can go from moles to that type of particle. And to do that, we're going to put Avogadro's number on the top and 1 mole on the bottom. And we can do that because 1 mole is equal to Avogadro's number. The same thing in reverse. If we want to change particles into moles, we'll put 1 mole on the top and Avogadro's number on the bottom so that would cancel. There is a second conversion we can do, and that's if we have some particle and that particle has atoms inside of it. For example, let's do C6H12O6. All right, let's say I knew how many of those I had. Let's say I have 14 of those. And I want to know how many hydrogens there are in 14 of those. All right, so I'm going from here to the number of atoms in the particle. So I would go 14 times, there are 12 hydrogens in 1 molecule, right? This whole thing's a molecule. So one of those has 12 hydrogens in it. So I could go 14 times 12 to figure out how many hydrogens were in 14 of those, okay, for example. So we'll use this later on in the lesson. All right, so let's look at some example problems back on the slideshow.
Kayla Gardner, you need to come to the front office, please. Kayla Gardner, come to the front office, please.
All right, so the first thing they ask us is how many moles of NaCl are there in 48 grams of NaCl? All right, so I'm going to kind of be flipping back and forth, so try to stay with me. I'm going to go to this where I'm going to write it out. So hopefully you can see this here. Here's the problem we're working. How many moles, so we're trying to go to moles, are there in 48 grams? And then this is important, it's NaCl. So the first thing you do is you write what you're given. 48 grams NaCl. And then you're going to write times and a line. That line tells you you need a conversion factor. And remember, a conversion factor is just a fraction that helps us change the unit. So we're going to put what we're trying to find on the top and what we're getting rid of on the bottom. And here's where the mole map is helpful. I have grams. I'm trying to get to moles. How do I do that? Let's go back to the picture. If you have grams and you're trying to get to moles, it says right here to put 1 mole on the top and the molar mass in grams on the bottom. So let's go back. I've got 1 mole on the top, and then I'm going to do the molar mass in grams on the bottom. So for sodium, the molar mass is 22.99 from the periodic table, and chlorine 35.45. Okay, so I'm going to add those together to get the molar mass for sodium chloride. .44 grams. All right, so you can see here grams is going to be divided by grams. So grams will cancel, and I'll just be left with moles. So 48 times, you multiply by the number on top, 48 times 1 divided by 58.44. So 48 times 1 divided by 58.44. And I'm going to answer to 2 digits, and I'll show you why. In the problem, this number 48 only has 2 digits, so my answer is going to have 2 digits. 0.82 mole of NaCl. So it's not even a whole mole, okay? It's 0.82 or 82% of a mole. All right, and we'll just keep moving forward here. Our next example is going to go from moles to grams. How many grams of C2H6 are there in 18.7 moles? So here we have moles, and we're trying to find grams. And this is important. This is the compound. So we're going to write down what we're given, 18.7 moles C2H6 times, and the line. Okay, to remind me I need a conversion factor. I'm going from moles to grams. So let's look at our map. From moles to grams, it's right here. I'm going to put the molar mass in grams on the top and 1 mole on the bottom. So molar mass in grams goes on the top, and then 1 mole goes on the bottom. For carbon, our molar mass is 12.01, and we're going to multiply that by 2, because we got 2 carbons, and then for hydrogen, 6 times 1.01. All right, so that's going to end up being 30.08 grams. All right, so here I have 18.7 moles times 30.08 divided by 1 mole. So moles divided by moles, so moles will cancel. So I'm going to do 18.7 times 30.08 divided by 1. That's going to be 560. Look here, they gave me 1, 2, 3 digits, so I'm going to answer with 3. 562 grams. All right, let's go to the back. How many water molecules are contained within a 56-gram sample? All right, so you got 56 grams of water, which we know is H2O, and we're trying to figure out how many molecules there are. All right, so let's look at our map. We're going from grams to molecules. All right, so when you look at the map, you'll see there's no way to go straight from grams over here to molecules. We've got to go from grams to moles and from moles to molecules. So first we're going to go grams to moles. So we're going to use this, 1 mole over the molar mass in grams. And then we'll go to molecules using Avogadro's number. Right? So back to our example. So the first thing the map said was 1 mole over the molar mass in grams. And then Avogadro's number over 1 mole. Okay, so I just pulled those two off the map. Now, when you have more than one step, you can just do them right in a row. You don't have to like stop and then do your second step. So you just put both your conversion factors. Let me look up my molar mass for water. That's going to be 2 times 1.01. And then my oxygen is 16.00. So that's going to be 18.02 grams. And then I have Avogadro's number over 1 mole. The way we have it set up here, we have grams on the top when we start, and then it's going to divide by grams, so those will cancel. And then moles is going to divide by moles, so those will cancel. So my unit that I have left is whatever goes with Avogadro's number, which in this case is molecules, because I'm talking about water. Okay, and water's particle is molecules. Right, so we're going to do 56 times 1 divided by 18.02 times 6.02 times 10 to the 23rd divided by 1. 56 times 1 divided by 18.02 times 6.022 exponent 23 divided by 1 equals. Alright, now I'm going to want this in scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Phew, yes. 1.8. Okay, they only gave me 2 digits in the problem. If you look back, they gave me 56, so I just need to give them 2 digits. So that's actually going to round to 1.9 times 10 to the 24th. And that is molecules of water. Alright, one more and we're done with this lesson, and then you can do some practice problems. This question is a continuation from the previous question. So the previous question said how many water molecules are there in the sample, and this question says how many hydrogen atoms are there in the sample. So here we have water, and this is asking me about hydrogen atoms. So if I go back to my map, minimize some of that stuff, we have grams, and we're trying to figure out the atoms inside the water. So we've got to go grams to moles, which we already did, moles to molecules. So we've already done that. So right now we have molecules of water, and we're trying to figure out how many atoms of hydrogen are in there. Well, how many hydrogen atoms are in a water? There's 2, right? So if you have 2 waters, you'll have 4 hydrogens. If you have 8 waters, you'll have 16 hydrogens. There's 2 hydrogens in every water. So when we look back, we can start our problem with 1.9 times 10 to the 24th molecules of water, and we're trying to get to hydrogen atoms. Okay? So hydrogen atoms are going to go on the top, and then water is going to go on the bottom. And then you're going to look at your ratio. There are 2 hydrogen atoms in every one of those water molecules. So water molecules will cancel. I'll multiply by 2 and divide by 1. So that'll be 3.8 times 10 to the 24th. Twice as much, right? Hydrogen atoms. So this word right here you'll have to be careful with. If you're talking about water, water's a molecule. So that number represents the number of molecules. If we're talking about hydrogen, it's an atom. So that represents the number of hydrogen atoms inside those water molecules. Alright, so there's an example of kind of each type. As you work, keep referring back to your mole map. Okay, figure out where you're starting and where you need to get to so you'll know what steps to take.